Thank you for reminding me. Okay, today is October 10th, 2022. We are proceeding with the topic on uniform circular motion, right? Just summarizing what we did so far. Here you go. We have a particle undergoing uniform circular motion, which is constant speed in a circle. And we want to derive the equations of motion of this particle. Here's the illustration of the particle in the circle of radius r. This vector position makes an angle theta with the x-axis. To find out the equation of motion, we have first get the coordinates x and y. X would be, r, right? Big R cosine of theta, and y would be big R sine of theta. Exactly what I have right in here. I still didn't get the equation of motion for x and y yet, because I have notice that my theta angle, is changing as time goes by, right? This vector position is changing as time goes by. Let's see here, just right in here, right? Here you go. Oops. Here you go. The particle is initially here and then move a little bit further away and so on, right? As the particle is moving in the circle, the vector position r changes. Okay. So this theta is changing with time. And then we must have a relation for theta. The very definition of an angle is given in terms of the length of the arc divided by r. That's how we define angles. Okay. This s here is going to be dependent on the speed of the particle. And this s here, let's see, it's increasing as time goes by, right? So here we go. A little bit later on, the particle is going to be here, right? So here we go. The angle theta is going to increase. The angle theta is going to increase. And this arc length is going to increase, and the particle is going to change its position at this point here in the circle, right? A little bit later on, the vector position again is going to change. Here you go. The angle is going to increase as well. The arc length is going to increase as well, s. Here you go, theta. And then there is one more thing. Because the particle is undergoing uniform motion, the speed is constant. This length, this arc length here is going to be dependent on the speed, and it's going to be linear with time. So this s that you see right in here is going to be what? Is going to be vt, right? Uniform circular motion. Means that s is increasing linearly with t. I am assuming that the initial angle at time t equal to 0 was 0. And now we have the equations of motion for the x and y coordinates in terms of the known parameters, that is v, r, and as a function of t. X and y as a function of t in terms of the known parameters v and r. Okay? That's the first set of the equations of motion for uniform circular motion. And then we do the same for the velocity. We do the same for the velocity, okay? So here you go. I'm going to copy all those 1, 2, 3 here. You go, those 3, 1, 2, 3, and I'm going to illustrate the velocity vector for those 3. The illustration of the velocity vector is going to look like that. I'm gonna change the color. Let's see, I'm gonna change the color of the velocity vector. Make it easier. Instead of red, we make it, let's see, green. Yeah, let's make it green. Here you go. And I'm gonna make my S red as well. I don't need the S anymore because now I'm gonna concentrate on this velocity vector. Okay. Okay, watch the velocity vector go. I'm going to go to the next slide, right? At this point in time here, the velocity vector is gonna change. The velocity vector is gonna change, but not the speed. So it's gonna change. Why is that gonna change? Because it's gonna make a different angle with the X and Y axis. Size, position, let's see here. Next rotation, here you go, I'm gonna rotate until this vector velocity is tangent to the path, right? You go, like that. In the next drawing, we're gonna do the same thing. And again, go. We have to change the angle of my vector velocity. Notice that the length of the vector is not changing because it's uniform motion, but the angle is going to change. The angle that it makes with the horizontal and the vertical is going to change. Position rotation, here you go. Let's make it tangent to the path. When I make it tangent to the path, it becomes perpendicular to the position vector, right? Becomes perpendicular to the position vector. And now we can visualize what's going to happen to this velocity vector right in here. The components of this velocity vector right here. Let's go back. Here you go. Here's the movie playing, right? Here. First frame, second frame, third frame, right? So what we're going to do, we are going to break down this velocity component into X and Y, okay? X and Y. This is the X component, this is the Y component, okay? Here is going to be theta angle, and here also is going to be theta angle. Let me run, here you go. I'm going to put a dashed so you can understand that this guy is there only for reference purposes. If this angle, here you go, this angle is theta, because this line is parallel to this other line here, it means that this angle also is going to be theta, right? Here you go, paste. One more student coming in, here you go. Theta, right? Here you go. I'm going to erase this guy here, otherwise the drawing is going to become too busy, right? If this angle here is theta, it means that this angle here is going to be 90 minus theta. if this angle is 90 minus theta, then this other angle here with the y-axis is going to be theta. Okay, and then I'm going to put another theta in there. Ooh. Let's see how I'm going to do that. Like that. Angle theta. And the way we represent that in mass, when we have similar angles, what do? We just put a little dash there, right? For all those angles to represent that those angles are the same. Like that. Here you go. And now I break down this velocity vector into x component and the y component. And we can see that the x component is minus, right? V minus because it's pointing from the left to the right, right? Here you go. Let me break down this velocity component here. X component is in this direction. Y component is in the vertical direction. And I'm going to dash those guys. 1 and 2. Let's see, I'll do this way so you can see it. Yeah, better now, right? That's Vx, that's Vi, Vy. The Vx is going to be negative because it's pointing to the left. The Vy is going to be positive because it's pointing upwards. So here we have minus V sine of theta. Sine of theta because the x component is opposite to the angle theta. So let's go ahead and we write it. V sub x is going to be minus V sine of theta, but we already know that theta is Vt over R, right? And the y component of, I did something wrong here. I shouldn't have done that. The y component of, I want to emphasize that's a plus sign here. Y component of the velocity, right? And then I just go back to what I had before here because I need this one. So here you go. Here are the equations of motion for the velocity of the particle undergoing uniform circular motion. Okay. Then there is the last one, the acceleration. How the acceleration is going to look like? Here you go. Here's the acceleration in the x direction, the acceleration in the y direction. Okay, let me copy this one. 1, 2, 3. Let's see here. Now I don't need that anymore. I don't want. I'm also going to erase the position vector because otherwise the drawing is going to become, oh, no. I got to keep the position vector in there because we need the angle, okay? We need the angle theta. Right? Well, how do we visualize the acceleration vector in there? Just remember that the acceleration vector always points towards the center of the concavity of the of the path. Okay, so here you go. Because what we have here is uniform circular motion, there will not be any acceleration component along the tangential direction. Okay, and all of the acceleration vector will have a component towards along the radial direction, not the radial direction, but against the radial direction. So here you go. That I'm gonna put that with a different color as well. It's gonna be blue. Okay, it is possible to derive that mathematically as well, but still, the book has the derivation for you. Okay, folks. You know, let me just flash that for you. But that's an easier way to understand how the acceleration vector comes about. The acceleration vector in this case takes the role of changing the direction of the velocity vector. Here you go. Let me show you here the derivation of the actual. Here you go. See here, he's putting the particle to move in a different way. Okay, v at time t equal to 0, v a little bit later. Notice that we have this initial vector velocity and the final vector velocity. What the acceleration is doing? The acceleration is changing the direction of the vector velocity. Because it's uniform circular motion, the length of the velocity vector remains the same. And then through a procedure, a geometrical procedure, we find out what's going to be the actual acceleration. Okay, I'm not going to do that because it's already in the book. Okay, but at least that you should know that the acceleration points towards the center of the circle, because the acceleration always points towards the center of the concavity of the path. Okay, here you go. No matter where you are located. Okay, just like this particle here, right? Here you go. This particle here, the acceleration is, I'm not gonna keep this guy anymore because there's no need to do that, right? The acceleration is gonna keep on changing its direction as time goes by. Go. In uniform circular motion, this acceleration is going to always be anti-parallel to the vector position. Because it is anti-parallel to the vector position, we can go ahead and, you know, take this guy here as a guide for the components of the x and y component of the acceleration, right? The only thing that we do not know is this guy, is the term that's going to multiply it by the, oh, I put sine here. It's not supposed to be sine, it's supposed to be cosine. Here you go. And here is going to be sine, here is going to be cosine. Oh, gosh. Nobody picked that up, huh? So, because this one cosine, this one is going to be sine. So what goes here in front, I'm going to tell you very soon. But let's not forget, it's going to be, you know, minus and minus. What's going to be here in front is going to be the magnitude of the acceleration, right? I'm going to put like that. And then we're going to find out exactly what is the magnitude of the acceleration. Makes sense? You know, because the vector position points away from the center and the acceleration points towards the center, the components, x and y components of the acceleration is going to be proportional to the x and y position with a negative sign here. We just do not know what, we still do not know what goes here. We know that's going to be the magnitude of the acceleration, but what is this value of the magnitude of the acceleration? Okay. Oh, this value of the magnitude of the acceleration is derived right here in your book, okay, in terms of geometrical parameters, and is given by this term right here, v squared over r. Can you memorize that? Okay. So, you know, using geometrical principles, in the book, we can find out that the magnitude of the acceleration vector is given by b squared over r. Okay, I'm using a different notation than the book is using. Okay, I'm using capital R for the radius of the circle. The book is using lowercase r for the radius of the circle. For the radius of the circle. And now we finally have our equations of motion for a particle undergoing uniform circular motion. You go v squared over r, v squared over r. Okay. Is that easy enough to memorize? Right? If you don't want to go through the trouble of deriving, it's not going to be difficult to memorize. Why is that? Well, because for x, all you've got to do is to know what comes here for x and y, and that can be, you know, figured out very easily just by projecting the r along the x and y axis, right? So you have cosine and sine for x and y coordinates. If you want to know the velocity, the cosine becomes sine, the sine becomes sine, the sine becomes cosine. And what was being multiplied by r becomes v, right? The multiplication factor becomes v. Let me emphasize here that r, and that's positive, positive and positive, right? Note, see that only the component along the x direction has a negative sign. Okay, only the component along the x direction has a negative sign. The component along the y direction has a positive sign. And then when you go to the acceleration, we get back what the trigonometric functions we had initially. For x direction is going to be cosine, x direction cosine. Y direction is going to be sine, y direction sine. What changes is the negative here. What was positive initially becomes negative here. And what else changed? What else changed is the multiplicative factor, v squared over r. Okay? This term, v squared over r, has a name. V squared over r, you know, is given a name. We call it not just the acceleration, but even better than that, we call it the centripetal acceleration, centripetal. Okay? ACP. ACP is called the centripetal acceleration. Centripetal means towards. Centripetal meaning towards the center. Okay? Now the center here. Petal towards the center. We have centripetal acceleration, right? We have centripetal acceleration, and we have centrifugal acceleration. Centrifugal meaning means away from the center. The difference between centripetal and centrifugal. Okay. So those are the equations of motion. Okay, so let's review that again. Here you go. Cosine, sine, cosine, right? Sine, cosine, sine. Plus, minus, minus. Plus, plus, minus. Here we have the same sign. Here we have the same sign. Here we have a mix of signs, negative and positive. All those terms that you see here, R, V, R and V squared over R, they are all positive. Right? R is the radius of the circle, has to be a positive all the time. V is the speed, is positive all the time. And what goes inside the parentheses is exactly the same term. Is the theta angle. What goes here inside is the theta angle that we here wrote it in terms of VT over R. Okay. That's what we have for the equations of motion, okay? The book doesn't have the equations of motion, okay? That is always good to. What we can do, we can come up with, calculate the centripetal acceleration. We can come up with examples of centripetal acceleration. Let's take a look at the examples of centripetal acceleration. Examples of centripetal acceleration. Okay, one example that I like to share with you is what is the centripetal acceleration of a point on the surface of the Earth located at the equator. Okay. What the centripetal acceleration do to the rotation of the Earth? Okay. Of a point at the Earth's surface, located on the equator, right? On the equator. Example. Solution. You gotta visualize this problem. And in order to visualize this problem, we have to draw. Let me see if I already have the drawing of the Earth here. No, I don't have it. I gotta do that from scratch. Too bad. Okay, so we have to visualize the Earth, right? Let's try to visualize the Earth here. Okay, here's the Earth. The Earth has a radius R. I'm not going to need the X and Y coordinate system for this problem. Okay, so we go. And I'm going to do something else. Let me see if I can get it. Don't forget, we're talking about someone at the surface of, at the equator of the Earth. Go. Nope. Yeah, I can do that. Okay, go. Let's see if I can get it, make a nice drawing of the Earth. Yeah. Make it a little bit thicker, right? Good. I'm gonna make this guy a little bit thicker so you can have the illusion that this is a three-dimensional object, three-dimensional sphere. Can I get it? No. One a little bit more. Yeah. Now I'm going to outline dashes the behind the part behind the Earth, right? The equator is here. I'm going to draw the higher latitudes as well. But we want to solve this problem only for the equator of the Earth. So you go here, going to be higher latitudes group. Right? Higher latitudes. Another northern, right? Northern hemisphere. Higher latitudes. They say, let's say here's 30 degrees latitude north, 60 degrees latitude north, and here the North Pole is 90 degrees. So we have our test subject that's right here at the equator. Okay, I'm gonna put it here. The vector position of this test subject with respect to the center of the Earth is this vector position here. Right here, okay. And we also have the axis of the Earth. Earth is rotating about this axis, right? Make it thinner. Yeah. North Pole is right in here. South Pole is right in here. The radius of the Earth is known. Okay? Okay, so we are going to do like that. What is the centripetal acceleration due to the rotation there at the equator, on the equator, right? On the equator. Use the values for use the period of rotation, the period of rotation, the period of rotation of the Earth is 24 hours, right? And its radius is what? The radius of the Earth. You can look at the book, or you can look in the internet. But it's around 6,400 kilometers approximately. Approximately 6,400 kilometers. If you want to know exactly, right? Let's take a look at the internet. Radius of the Earth. Oh, 6,371. Man, I came close, didn't I? 6,371. 71 kilometers on the equator. Okay, solution. Okay, we start with the equation for the centripetal acceleration. It's v squared over r. Oh, here you go. I already have it here. I'll put it again. A centripetal equal v squared over r. We do not know the tangential velocity of the Earth, right, at the equator. Here at the equator, you must have a tangential velocity. It's somewhat like that, right? If you look from the top, looking from the top, make it easier to visualize that. I'm going to look from the top. Oh, not this one. Here you go. I want this one here. Oh, this one, this one, this one. Here you go. Looking from the top, my particle is right in here. The North Pole is right in here. Okay, got it. My vector position, that's my vector position. Is this one? That's the vector position. And the velocity vector of the particle on the equator is here, right? Different latitudes, you know, I want to illustrate different latitudes here. Ooh. I have presented this way. You go, one latitude. Transparency, here you go. Another latitude. So on, right? Because of the effect of latitude, the vector velocity at different latitudes should be lower than at the equator, right? And we're going to look into that too very soon. I'm going to make it a little bit thinner. Yeah. Thinner. Right? So that's where Santa Claus lives, right? North Pole. So that's, let's see, 0 degree latitude. That should be roughly 30 degrees latitude. That should be roughly 60 degrees latitude, 90 degrees latitude. Now, we do not know what is this tangential velocity here, but we can calculate it. We do not know what this tangential velocity is, but we can calculate it. We can calculate because we know the radius of the Earth. And we know the full period of rotation of the Earth, 24 hours, right? So here you go, going back here. V is going to be what? V is going to be the full circle, 2 pi divided by the period of the Earth. Here you go. 2 pi r. I forgot 2 pi r here. Here you go. 2 pi r divided by the period of the Earth. right? That's what V is. Make sense? 2 pi r is the full circle, right? The full circumference. Full circumference. Length divided by time is the velocity. That's how we find out the velocity. And then, you know what I'm gonna do? I'm gonna run a computer program here for you to make it easier for me to calculate this number. Okay, I like to use the software here to do that. It's an algebraic manipulator software that you can place number that you can use to calculate numbers there, values as well. I could do that with Excel as well. So here you go. Centripetal acceleration is equal to what? You know, 2 pi r, 2 pi r over t, period of rotation of the Earth. All of that must be squared, divided by r, right? I didn't go the next step. I will go the next step here. I'm going to expand everything. Yeah. Okay. Do you see what happened here? The 2 was squared, the pi was squared, the r was squared, but the squared r would cancel out with r. That's why I have a single r here, divided by t squared, right? And now I'm going to substitute the numbers. Here you go. T is going to be 24 hours, right? 1 hour is how many seconds? Remember, you gotta always change it to the main units of SI units, right? 1 hour is 3,600 seconds. R of the Earth is what? The radius of the Earth is 6,371 kilometers, which, by the way, is 1,000 meters. And with all this values, we can start calculating the numerical value of the centripetal acceleration at this equator of the Earth. I am substituting r in there. Here we go. Okay, t is 24 hours. I put 24 hours there, but we have to change the hour to seconds. Let's see here. Didn't like that. Yeah, now I have it. Now you can do it. Okay. And I go ahead and do my calculation, expand. This guy is approximately 10. Let me get the calculator. Yeah, here you go. Pi squared is approximately 10. That's why we ended up subtracting 1 decimal place. That's the centripetal acceleration due to the Earth's rotation. If I did everything right, I got the right numerical value for the centripetal acceleration, which is, you go, 0.0, just one, right? 0.03363, let's put 337 meters per second squared. Okay. .337 meters per second square. This centripetal acceleration is going to be different for different latitudes because we have different radius for this circular motion, right? Going back here, right? So here you go. Take a look at this one. See that? This guy at the equator has a different radius for the circular motion. Now, this other guy at higher latitudes is going to have a different radius as well. All right, here you go. This other point here is going to have a different radius as well, and a different velocity vector as well. It will undergo a shorter distance in the same amount of time. So the velocity vector, here you go. The velocity vector is going to be slightly shorter. Okay, here you go. At higher latitudes, it's going to be right here. I have to shorten up this vector position. I have to shorten up this velocity vector. Okay, and the radius of the circle is going to be dependent on the latitude of the place. So people at the equator is subjected to a higher centripetal acceleration than people at higher latitudes. Okay, that's one example. We can come up with another example. Okay, let's see, 9:42. Let's see if we can finish one more example here. Let's take an example from the book, so you can get familiar with it. Example, let's see, example 1, example 2. Let's do this example 3. No, I don't want to do this one. I want to do a more. Echo, this one. No, not this one. Centripetal force. Okay, so let's see. Oh yeah, let's do the bobsled. Okay, this one here. Here you go. Let's do this one here. The bobsled track at the 1994 Olympics, Lillehammer, Norway, contained turns with radii of 33 meters and 24 meters. Okay. Find the centripetal acceleration each turn for a speed of 34 meters per second, a speed that was achieved in the two-man event. Express the answers as multiples of g. Okay. So let's transport this to my, another example, example 2. We have two radii, right? One radius of 33 meters. Another radius. What's the other radius? 24 meters. The speed is what? 34 meters per second. 34 meters per second. 34 meters per second. Right? So here we go. Find the centripetal acceleration at each turn. Okay? So here you go. Here's the track. You can visualize, right? And the bobsled undergoes a turn of a radius of 33 meters, a second turn of 24 meters. Find the centripetal acceleration on this turn, find the centripetal acceleration on this turn. Okay? Find the centripetal acceleration at each turn. Solution. That's straightforward, right? Just straightforward application of formulas, but then he asks us something else too. Find the centripetal acceleration in terms of g. That's what he's asking. Right, go back to my software here. Here you go, centripetal acceleration equal. You can do that with your calculator. You can do that with Excel, or you can do that with any other software you have out there. V squared over r. But now my v is what again? 34 meters per second. we have two radius, R1 equal to 33 meters, R2 equal to 24 meters. I'm gonna put, here you go, those three below my acceleration. Okay, I substitute 34 meters per second here. Now my centrifugal acceleration becomes something like that. Take this square and we get something like that, but I still didn't substitute for the radius. Let's substitute for the radius now. All right, so here you go, substitute for the first radius. Ah, interesting. Yeah, I gotta rewrite my equation here. Have to rewrite in terms of R1. Right, I have to rewrite in terms of R1 and R2. You go. That's the oh man, he's not calculating that. That's unfortunate. Let's see why he doesn't do that. Clarify, simplify, expand. Yeah, see, I hate when that happens. Well, there's a little trick that I can do with this software. Now I can calculate it. It's kind of annoying, but okay. So that's the acceleration that I get for the first term, 35 meters per second square. Then I'm going to calculate for the second term. It's better if you put just below it here so it's well organized, right? Second term, here you go. Let's see if it calculates or not. Expand, no, just like before. I'm gonna do that little trick here to get the software to calculate those values for me. Expand, good. No, didn't calculate. Expand, oh man, gotta calculate it. Expand doesn't work. Here's the other acceleration value. Okay, the first acceleration is 35 meters per second square. The second acceleration is 4.8 meters per second square. I'm gonna copy. Okay, copy and paste it. First one for R1. For the first turn, we have for the second turn, we have, no, you go, one here. Like that. You go. But that's not what he asked. He didn't ask for the value of the acceleration, of the centripetal acceleration. He asked the value of the centripetal acceleration in terms of the G's, okay? In terms of the acceleration of gravity, which is approximately 10 meters per second square, 9.8, right? Let's use 10. That's easier, right? How many G's do those values represent? Okay, this value here represents roughly 3.5 G's, which is 3.5 times your weight, okay? And this other one here is almost 5 G's. It's 4.8 G's. 4.8 G's, okay? Which is very grueling to be subjected to. 3.5 is already difficult. 3.5 is already difficult to stand, and 4.8, almost 5, is even more grueling to stand. So those athletes They must be trained to sustain these types of acceleration. It's like, it's like dealing with 5 times your weight. That's what it's all about. Here's almost 5 times your weight. Here's 3.5 times your weight. Okay. So it's 9:50 right now. Any question? Let's go for our break, okay? And break, 15-minute break till, let's see, till 10 a.m. Okay. So I see you in 15 minutes. Thank you for reminding me. We already missed a big chunk of what we said, right? Let us review so it stays in the recording. Let's review so it stays in the recording. So here you go. We have the situation in which I think we're doing example 5. Example 5 is the case of a model airplane. Here you go, a model airplane attached to a line, to a guideline. This plane is undergoing uniform circular motion. The guideline is in the same plane as the plane of motion of the airplane. The airplane has this mass of 0.9 kilograms. The length of the guideline of the string, right? The guideline is the string, is 17 meters. What would be the tension in the string if the speed is 19 meters per second and 38 meters per second? Notice that one speed is twice the other, okay? Notice that one speed is twice the other. And again, we came up with a free body diagram. First, we illustrate the airplane in this from the top, right? From the top, the guideline attached to the plane undergoing uniform circular motion. And then we start looking at the airplane under this angle here, at the plane of motion of the airplane. Airplane, weight applied to the plane, lift of the wings applied to the plane, and the tension in the guideline applied to the plane. That's what we call the free body diagram. The lift cancels the weight because the airplane is not accelerated upwards. That's why, because the airplane is not accelerated upwards or downwards, we can say, according to Newton's first law of motion, the lift is equal to the weight. Okay? And we are left with this tension. I'm gonna put a tension like that. Tension in the string, in the guideline. So we go ahead and use Newton's second law of motion right in here. Newton's second law of motion is right in here. Right? Net forces mass times acceleration. Because uniform circular motion, so we have a centripetal acceleration. Because we have a centripetal acceleration, we have a centripetal force as well. But looking carefully at the situation, we recognize that the centripetal force must be equal to the tension in the string or guideline, which is mv squared over r. And now we want to solve this problem for 2 different speeds. V1 equal solve problem, right? For V1 equal to 19 meters per second, right? And V2 equal to 38 meters per second. What's going to happen to the force? The speed increased by twice. Do you expect that the tension is going to increase by twice if the radius remain the same? Not so, right? Not so, because the speed goes, the tension goes with the square of the speed. If you double the speed of the plane, the tension is going to increase fourfold. Make sense? Okay. So let's go ahead and solve this problem. Here you go. Another situation here. Here you go. Tension is equal to mass times centripetal acceleration. Right? Centripetal acceleration is v squared over r. And then we have all those values for the mass, 0.9 kilograms. R is what, 17 meters? Let's take a look. 17 meters. 17 meters, yeah. And then we want to do for, when I solve this problem for two different speeds, 19 meters per second and V2, 38 meters per second, two different speeds. Yeah, organizing here. I'm going to replace, I'm going to substitute here for the mass and the radius. When I do that, I can drag the tension to that spot, right? And then we gotta have V1 here, right? V1, and we have to have for the other one V2. Let's see how much force requires to keep the plane. Here you go. That's expand. Yeah, calculate. Note, see, we got 19.1 newtons, right? Kilograms meter per second squared is a newton, right? Is a newton. Here you go. 19.1 newtons for this speed here. What about the other speed? Let's substitute V2, expand, 76 newtons. You know, like I told you, it's fourfold, right? Fourfold, 4 times. We double the speed, the force increased by fourfold. So you gotta be careful not to you have to be careful to use a string that can sustain that much force. If you use a string that's not strong enough, the guideline is gonna break and I'm gonna lose your airplane, your model airplane. Okay? So I'm going to, here you go, copy and paste it here. That's one example. There's another example that I like to discuss with my students. Here you go. You know, what does it mean to have that much tension? Well, it means that if you put a scale, right? If you attach a scale here in this string, that scale is going to indicate a force that's going to be given by that, right? By that value that we calculate, 19 newtons and 76 newtons. Let's take a look. I don't want to do this. Oh, let's take a look at this one here. This one, the case of the car in a turn, right? In a closed circuit. Yeah, centripetal force and safe driving. Let's see if we can take advantage of that. At what maximum speed can a car safely negotiate horizontal? None. Nope. At what maximum speed can a car safely negotiate horizontal unbunked turn in dry weather? The coefficient of static friction is 0.95. And nice weather. Two different circumstances. Okay? Dry weather has a given static friction, and icy weather has a far more different coefficient of static friction, 0.1. Whoever has driven under icy condition knows how difficult it is to keep a car in the turn, right? You have to go very slowly. It's not just icy condition, it can also be a wet surface. Okay, so let's go ahead and we're going to use the same drawings that we used before. Now, instead of a plane, it's going to be a car, right? Here you go. A car, here's the radius. The radius of this one we can put a arrow there. Nope, not this one. It's this one here. Here you go, arrow. I'm going to put lowercase r to indicate this is a vector. Okay, so let's extract all the information that we want from that problem, right? Another example, that's example 7. Example 7. Okay, radius 51 meters. Ooh. Two coefficients of static friction. That's going to be mu1, mu1 equal to 0.9 or 0.95. Let's take a look. Oops, equal 0.95. 0.95 and another coefficient of the static friction. Let me change to symbol. Go. And this one's supposed to be subscript. Go to the other one under icy conditions. Find maximum speed. And by the way, this coefficient is going to be coefficient of static friction, okay? I'm going to tell you exactly why is that. It's not obvious. Why is this coefficient of static friction? Find maximum speed. To safely negotiate the turn. Solution. Okay. So again, we gotta come up with our free body diagram. Okay. We have this vector velocity here. We are assuming again uniform circular motion. Okay. We're still assuming uniform circular motion. Find maximum under UCM, under uniform circular motion. They didn't say that, right? But that's what it's supposed to be. What maximum speed can car safely negotiate horizontal unbunked turn? Okay, bunked turn is different in dry weather and icy roads. Okay, that's one way. Here you go, and then we are going to come up with another view of my car, right? Let me see if I have it. I have it. I think I have for the, yeah, I have it here. I don't need to keep on drawing that for you. Okay, here you go. What's Vmax? Okay, so here's my car, right? And here you go. Here's a drawing. Remember, here's my car. Now I'm looking at the car in the plane, in his plane of motion, the direction of his plane of motion, right? parallel in the direction, parallel to his plane of motion. I have to recognize, I have to determine what are the forces that are applied to the car. The first force that's all the time there is the weight. The other force is the normal. But the car doesn't move in the vertical direction, just like the plane, right? So it means that those two forces are going to cancel each other. The normal force is going to cancel out the force of the weight. Because the car is undergoing uniform circular motion, you must have a centripetal force. Now, the question is, who is this centripetal force? Okay, so I want to ask you, give me, who is this centripetal force? What's the centripetal force that's going to keep this car in this circular motion, right? In the case of the plane, it was the tension in the wire that kept the plane in a circular motion, uniform circular motion. But in this case, you do not have a string attached to the car, right? We do not have a string attached to the car. So it must be a different force. Which force would that do you think that's going to be? It's not obvious, okay? If you're seeing this problem for the first time, it's not going to be obvious for you. Think about that. The problem gives you a piece of data, which is coefficient of static friction, right? The coefficient of static friction. So he gave you, in a way, he gave you a hint of how to solve this problem. Let me see if I have the next one. Oh, yeah. So what is this centripetal force, right? So I'm going to come up with this. Here you go. Because the car is moving under uniform circular motion, we must have a centripetal acceleration, right? And because we have a centripetal acceleration, we must have a centripetal force. On the top of that, we must identify what the centripetal force is. Okay, there's a little secret here, okay? This centripetal force, by the way, is going to be the force of static friction. Why is that? Why is that? Okay, if we did not have any static friction, if we didn't have any friction between the tires of the car and the surface, the car wouldn't be able to perform a circular motion, but just would move in a straight fashion, like a straight arrow. That's all. But because there is some friction right in here, okay, at the tire of the car, the car manages to stay moving in a uniform circular fashion. Okay, and this force of static friction is applied towards the center of the circle. So that's the little secret that you have to remember when solving this problem, this type of problem. Yeah. Gotta bring this guy up, bring to the front. Here you go. Now I don't have any problems. Bring to the front. Bring to the front. Good. Now here you go. Now you can see my. Let's not forget that the force of static friction has values between 0 and a maximum value. Remember that? Okay, so that's the little secret that you have to keep in mind. Okay, first, here you go. First, make a drawing of the situation. Next, identify the forces. Normal, weight, and a centripetal force that you should not know. You should do not know. which one it is, it is, okay? Okay, it happens that the car manages to stay moving in a circle because of a force of friction. If there was no force of friction, then the car would not be able to remain in circular, to stay, circular motion. Okay. Consequently, but there is more to it, right? Why is static friction? There's a reason why it's static friction. It is static friction because the car is not moving away from the center of the curve. The distance from the center of the curve remains the same no matter what. That's why it has to be a force of static friction. Okay, that was exactly when you're turning your car around the curve, right? When you're negotiating a curve with your car, do you hear that sometimes the tire is screeching, right? If you're moving too fast in that curve, the tires of the car start to screech, right? So what's happening that the tire of the car starts screeching? It means that the car is moving away from the curve. Okay, you're breaking through the force of static friction, and it becomes, instead of force of static friction, becomes kinetic friction. Okay, you don't want to do that in this problem. You want to ensure that you stay within the values of the force of static friction. So here we go. Now we repeat the same thing, the same idea, right? Centripetal force equal, well, net force is equal to centripetal force, right? Centripetal force is equal to mass times centripetal acceleration, mv square over r. But now you also have that this centripetal force is equal to the force of static friction, which, by the way, is going to be equal to mv square over r. Furthermore, you also know that the force of static friction can be greater or equal than 0. Right? Remember, we went through that before. Greater or equal than 0. And it can also have a maximum value that I'm going to write down as being force, maximum value of the force of static friction, right? Here you go. And by the way, this maximum value of the force of static friction is equal to what? This maximum value of force of static friction is equal, let's see here, mu, okay, is equal to the coefficient of static friction times the normal. Okay, you already know that the normal is canceling the weight. Consequently, we can here write that at mu sub s and g, and we get this inequation for the force of static friction. Okay, but remember, we have this equality here for the force of static friction, so we can use this equality equation for the equality of static friction in this inequation here for the force of static friction, right? So here you go. All I have to do is to replace this force of static friction with this value that you see right in here. There is a equality there that I am using in this inequality. There is an equation here that we are using in this inequation, right? This is an equation, this is an inequation. And note that this value can take any, this equation here can take any value between 0 and this maximum value. If the mass is constant and the radius is constant, what does it mean? It means that the velocity can be anywhere between 0, can be, and this, and a maximum value given by this equation, okay? And now we have the maximum speed that you can drive to ensure that you can, oh gosh, that you can negotiate that turn safely. This become an equal sign because we are using the maximum value of the speed, right? And we solve this equation, V max square R over M, right? Because note, see that R, the mass cancels out in this equation. So the maximum speed does not depend on the mass of the car. Doesn't matter if it's a very light Honda Civic or a very heavy truck. And your maximum speed, the one you will be able to safely negotiate that freeway exits, right? That are usually very tight. You go, the max. Oh no. You go, it's gonna be given by that value. Now I have my genetic equation that I'm gonna put there in my software, my favorite software. It's time to go for a break very soon, right? You go, V max equal to the square root of mu s, what else? G, oh, G, right? No, G here. We have something else there. Over R. No, mu s G R. Radius. Mu s, right? Yeah. So we have two situations. Mu sub S1, that's dry pavement, 0.95. And we have the second situation, mu sub S2, that's not dry pavement, is a icy pavement. Which one? Let's solve for the guy ones, these ones first, right? And I also have, go G, I'm gonna use 10 meters per second square just to make things easier, okay? There's no D here. What else? R, what's the radius of curvature of the turn? R is 51 meters. R is 51 meters. I put lowercase r, supposed to be uppercase r. 51 meters. I can, okay, negotiating. Okay, R. One more G here, and now we have to apply for two different conditions. Okay, one dry pavement, the other icy pavement. Let's compare how bad it is to drive an icy pavement. Right? There you go. Now let's see how we can do that. Yeah, let's see. And let me see if I can expand. Okay, he does it for me. That's good. I don't need to do any special tricks here. But I might need to do a special trick here. No factor, maybe. No. Simplify, expand, collect. No. You know, that's meters per second, right? Sometimes the software doesn't do, oh, he did for meter, but he didn't do for meter per second square. The software didn't used to do that, by the way. Used to be far more. Okay, so that's what we get, okay? It's 22.01 meters per second. Let me simplify it. Yeah, it's supposed to be meters per second, okay? This guy here, yeah, too bad. Here, sometimes we have, that's for the first situation, dry pavement. Now, what about icy pavement? Icy pavement. Huh. That's so sad. Like that. Go. 51, right? And now he will be able to give me a result. Here you go. Square root of 51. What's the value of square root of 51? Is 7.1. See how much, what's the difference here from pavement and the other? Icy pavement, dry pavement is a huge difference in speeds. Okay, so it's 11:04. We need to go for our break right now. Do you have any questions? Okay, so let's see. I'm gonna give you opportunity for, let's see. Ana Lopez, are you there, Ana Lopez? Ana Lopez is no longer here. Yeah, Ana Lopez is no longer here. Okay, what about Raymond Garcia? Are you there, Raymond Garcia? Okay, thank you. Here you go. So now we have 20. There must be another student here because we have 23. Okay, who was not called, by the way? I don't see Ana Lopez here. Fisher, are you there, Fisher? No, let's see. Lily's not here. Wendy, are you there, Wendy? Wendy and Joshua? No. Luis and Ana Lopez? No, I don't see it. Elika? Are you there, Elika? No. Justana? Justana Youssef? Nope. Okay, so okay, it is whatever it is, right? So let's see here. Yeah, good. So let's go for our break. Break till 11:20. I'll see you in 15 minutes. Here you go. Okay, there's a class of problems called the apparent weight problems. You have, so you have your actual weight, which is your mass times the acceleration of gravity that you are subjected to. And then in real life, you also have what we also have what we call the apparent weight. The apparent weight, your apparent weight can be either more or less than your actual weight. Okay. It's the case, for instance, an example, a typical example is the case of astronauts in weightless. Those astronauts, they experience the condition of weightless, okay? Which, by the way, which is a special type of apparent weight. Which is special type of apparent weight, okay? Which is special type of apparent weight. But then you have the other way too. You can, by the same token, you may have a weightless condition, right? You can also have a heavy weight condition, okay? You can have situations in which you feel heavier than you actually is. You have situations in which you feel heavier than your actual weight, okay? That can be done, that can be done by this, these conditions of apparent weight can be simulated by using an accelerated frame of reference, okay? By what I mean by accelerated frame of reference, by accelerated frame of reference, I mean an accelerate or an accelerated enclosure or car, like the one in a roller coaster. Okay. I'm going to give you some examples of that. Let me see if I have an illustration here first, so I can share that with you. Oh yeah, here you go. I have here. Here you go. That's an illustration of the condition of weightlessness. Okay. We can simulate this condition of weightlessness here on the surface of the Earth. You don't have to go to space to simulate this condition of weightlessness. That's the case, for instance, of an elevator. What we have here, someone inside an elevator, right? An elevator that the cable of the elevator broke and the elevator starts falling. Free fall. You have the condition of free fall. When you have a situation like that, the weight of this guy becomes 0. Okay? The elevator is accelerated downwards at 10 meters per second square, and you feel weightless. But you can also have this situation here, in which the elevator is accelerated downwards, not at 10 meters per second square, but let's say at 20 meters per second square. In this case, the acceleration becomes, your weight becomes negative, start pulling you upwards, so much that you can stand on the ceiling of this elevator. Okay, and then you can have everything else in between. You can have the elevator accelerated upwards, so you feel heavier, and so on. Okay, so here you go. And this type of problem we solve by using Newton's law. You know, I was supposed to solve this in the previous chapter, but I didn't solve it because I want to tie that with the next type of problems of uniform circular motion that we're going to see right now. Okay, so let's come up with an example here. Let's do an example. We are going to do an example on apparent weight. Okay. So the situation is the following. Consider an elevator that is accelerated upwards at 10 meters per second square. Okay, what is the apparent weight that an occupant, an occupant of mass M feels inside this elevator? Okay, so that's example, apparent weight example, and then we're going to use those same ideas, apply it to uniform circular motion. Okay, we apply Newton's law to solve this problem. So the situation is the following. I'm going to come up with just like before, I'm going to come up with a free body diagram. Okay, let's start with the simplest type of drawing, and then we are going to build it, you know, to make it more difficult, to elaborate on that. Okay, so here you go. The situation is the following. We have the acceleration of gravity, and for this problem, not only you have this acceleration of gravity, but the elevator is also accelerated upwards with an acceleration of equal to g, 10 meters per second square. Okay, so I'm gonna put this guy right in here. What I'm doing here is just to remind you that that everybody's being subjected to the acceleration of gravity. So we have this occupant of the elevator that's weighting himself, weight in a scale. Okay. And the key here is to figure out what would be his apparent weight under this condition. Okay. Find his apparent weight. Okay, so the first thing you gotta do is to figure out what are the forces that are being applied to this occupant. Okay. The first force that comes to mind is the weight. Oh, cannot do that. Can do this one here. The weight is always there. The occupant has mass m. Okay, so the weight is going to be downwards. But now, don't forget, this guy is standing on the top of a scale. He doesn't have to stand on the top of the scale, but I'm putting there the scale just for the sake of discussion here. Not only we have he's subjected to the force of the weight, the force of gravity, but he's also subjected to another force that we call the normal, right? Free body diagram. The normal between normal is the force that between the scale and the occupant. So what we are going to do here, let's see here. We start with this one. I like to do step by step so I do not overwhelm you with too much stuff, right? That's the first slide. That's the second slide with the weight in there. That's the third slide with the normal. And now we apply Newton's second law of motion. Okay, applying Newton's second law of motion to this situation. We have, here you go, net force is equal to mass times acceleration. It's not uniform circular motion, so you do not need any centripetal force in there, right? Here you go. And then what else do we have to worry about? Okay, so the net force in this case is going to be what? The net force is going to be the normal minus the weight of the occupant. Okay. Now there is a little trick here, right? Because the elevator is accelerated upwards, something interesting is going to happen. You know, the normal is going to become greater than the weight. Have you ever experienced that in an elevator? You are at the bottom of the building, they're inside the elevator. The elevator is initially at rest. The elevator starts to move. What does it happen? It starts from rest, start to move upwards. It is accelerate for a small amount of time. What do you feel? You feel that you become momentarily heavier. And what does it mean? It means that the normal became greater than your weight. Okay? That's what happens in those situations when the elevator is accelerated. When the elevator starts, stop being accelerated and start to move with constant velocity, then the normal becomes equal to your weight and you have your regular apparent weight there. Okay? But here is a different elevator. It's an elevator that keep on accelerating, that stay accelerated, keep on changing its speed to ever higher and higher speeds, right? And that's what we end up getting. And then there is one more thing. A little secret, right? That is not easy to recognize. Your apparent weight, whatever your scale is going to indicate here, what of your weight is in reality coincides with the normal that the scale is applying to you. Okay? So the normal itself, in the case of this elevator, is a measure of your apparent weight. Okay? So here you go. For these types of problem, the normal itself is a measure of your apparent weight. Okay? So if you want to know your apparent weight, all you have to do is to calculate the normal force. This normal force that you see right here, okay? Solving this equation, you get what? N equal to mg plus ma, okay? Which, by the way, becomes, you can put in evidence, okay, it's going to be greater than mg. In this specific situation, you feel heavier because your apparent weight, or the normal that's applied to you, is greater than your regular weight, than your regular mg. We can do the other case. We can do the other case in which the elevator is accelerated, not upwards, but downwards. It's accelerated, here you go, downwards. Downwards, let's say 5 meters per second squared instead. Let's not do 10 meters per second squared yet. What's the apparent weight that an occupant of mass m feels inside this elevator? Okay, just like before, we go ahead, come up with a free body diagram, but the difference being that now the acceleration is going to be downwards. Okay, I'm not going to put a equal to g. Right, I'm going to put a, just a. Once you do that, you have to come up with this free body diagram. Okay, recognize that we have the occupant is subjected to the weight, to his weight, her weight, but also subjected to the normal force. Okay, I am, by the way, we go. I have, let's see here. Yeah, gotta get this one here. Copy this one, right? And place here. Here you go. Now I have it. Now I have it right. Just like before, we're going to apply Newton's second law of motion, okay? You know, but be careful here in this case. In this case, the acceleration is downwards. If I consider the upward direction as being the positive one, so what do I have to do is my acceleration here? I have to make it my acceleration negative, right? And solve the equation accordingly. Here you go. mg minus ma, mg minus ma, and look what we get. You know, we get, you know, a normal that's less than mg. In this specific case, it was an acceleration downward, you're going to feel lighter. If the acceleration matches the acceleration of gravity, if the acceleration is g, then you're going to feel weightless. That's the case of problems that involve apparent weight. And now I'm going to apply those same principles to uniform circular motion. How do we do that? Okay, the situation is the following. So, you know, when you go home, you know, think about that, about this type of problem, learn it well, understand it well, how to do it, okay? And now, let me see here. Let's go down. I don't have it, unfortunately. I have got to do that from scratch. Yeah, looks like I have to do from scratch. What a shame. I used to have all those things in my slides. Yeah. They must be they must be hidden somewhere here in my notes. But I'll do that. I'll draw that from scratch. Let me see if your book has that. So no. Banked curves. Yeah, I'll have to make it up. Yeah, I have to create my own examples so you can. Yeah, here you go. That's a nice problem as well. Physics of artificial gravity. Yeah, okay, here you go. That's what I want. I want a problem like that. Okay, so here you go. I'm going to formulate the problem here. Another example. Example involving apparent weight and uniform circular motion, okay? That the Ferris wheel of radius r rotating Ferris wheel of radius r rotating undergoing uniform circular motion, UCM. We have an occupant inside Ferris wheel. Undergoing UCM, uniform circular motion with speed v. Have an occupant inside the Ferris, riding. I have an occupant riding right along the Ferris wheel. What is his apparent weight at the bottom and top of the trajectory? Okay. At the Ferris wheel. Here's her apparent weight, right? So think about that, how the problem is. So here you go. We have a situation like that. It's going to be slightly different than what we're talking about, just about the bottom and the top of the Ferris wheel, right? So what we have the chair, right, of the Ferris wheel that moves along. Can someone sit down here? And you go, no fill, you go. I'll make a little bit thicker so you can. So let's say, the guy is either sitting down or standing up. Either way works, okay? Either way works. I'm gonna put him standing up so it's easier to draw for me on my side. And not only he's standing up, but he's standing up in a scale that measured the normal force that's being applied to him. So remember, in order to solve this problem, first you have to understand you have to know how to solve the other problem that we covered, right? The one-dimensional one. And to make it look better, here you go, like that. Radius R. Oh, no, this one here. Speed, right? Uniform speed. So I want to know the apparent weight here at the bottom and the apparent weight here at the top, at both positions. Okay, here at the top and at the bottom. Okay. So what you have to do, right? Just like before. You have to look at the forces applied to the occupant there in the Ferris wheel group. I'm gonna group this guy here. Here you go. Bottom, right? What are the forces applied to it? Okay, first, definitely we have the weight. And by the way, I have to give you also the information of the mass of the individual. Let the Ferris wheel run. We have an occupant of mass M riding along the Ferris wheel. What is his apparent weight at the bottom and top of the trajectory? Okay. Here you go. We have the weight, and we have the normal as well. The normal is not going to be necessarily equal to the weight. That's because now this guy is accelerated. Let's not forget that at the bottom of the trajectory, what's the direction of the acceleration at the bottom of the trajectory, right? Think about that. What's the direction of the acceleration? This guy is undergoing uniform circular motion, right? Consequently, his acceleration here at the bottom is going to be upwards. Make sense? That's the case at the bottom. Okay. I'm going to put this here. Yeah. So I can write that down here. That's what's going to be his acceleration upwards. Here's going to be the weight, mg, and the other one is going to be the normal, n. And you go ahead. There is no other forces applied to this guy, just the normal and the weight. And now we set up the equations for Newton's law. Okay, so what are the equations? Always referring to this drawing. 6 more minutes to go. Okay, so here you go. Net force is equal to what? Normal minus mg. In this case, the acceleration has the same direction as the normal. Consequently, the acceleration must have the same sign as the normal on the right side of the equation. Okay? And let's not forget that we also know the velocity of the Ferris wheel. Oops. The velocity of the Ferris wheel. Did I write that down here? Yeah, speed m, speed v, v squared, and the radius of the Ferris wheel as well. Right? The acceleration is going to be the centripetal acceleration in this case. The net force in this case is going to be the centripetal force in this case. The acceleration is going to be the centripetal acceleration in this case. It just happened that at the very bottom of the trajectory, the acceleration coincides with the y-axis. It's going to be upwards. Okay, and we have the normal equal to normal minus mg equal to that. We solve for the normal to get the apparent weight, and we get an apparent weight that is slightly more than yours, than your regular weight, than your regular mg weight. Okay. You feel heavier. At the bottom of the Ferris wheel, you feel slightly heavier. What about at the top? Okay. At the top is the contrary, right? It's the opposite. Here you go. Here it's gonna be at the bottom. I'm gonna write that down here, bottom. Three more minutes to go. I'll try to finish that in 3 minutes. What about the top? Top. Okay. At the top is going to be the, we're still gonna have a normal. We're still gonna have mg. The only difference at the top is going to be what? The acceleration. The acceleration is going to be downwards, right? The acceleration is going to point towards the acceleration, centrifugal acceleration always point towards the center of the trajectory. At the top, it's going to point downwards, but at the bottom, it's going to point upwards. Make sense? So for this case here, at the top, the acceleration is going to be downwards. And what's going to happen to your weight? You're going to feel slightly lighter. Okay, that's top, bottom of the Ferris wheel. Top of the Ferris wheel. Because the acceleration is downwards, it must have the same sign as the weight, right? So it's going to be a negative value here, a negative sign, and what's going to happen? You're going to feel it's slightly lighter. You feel it's slightly lighter. So those are the type of problems we have for apparent weight involving uniform circular motion. Okay. 1 more minute to go. Do you have any questions? I'm going to come up with your homework for this chapter. So watch out for new homework for the chapter on uniform circular motion, and I will see you again on Wednesday. Thank you for being here.
Thank you.
Welcome. Thank you all. By the way, I have office hours now, right? So if you want to stick around, you can stay around. If you want to stay around to ask any questions, you can do that. If you need any help with your homework, anything like that.